Okay, hello everyone. Good afternoon or good morning, everyone. So today is our last day for this workshop from JCIOI, and for the second online workshop on ice-ocean interaction. And last section is talking about the meltwater happening here. That is the impacts of the meltwater on ocean circulation. And here today for this session, we have two keynote speakers, Torge and Tor, and they will talk about separately about the meltwater from Greenland and also the meltwater from Antarctica separately. So the first session is about the keynote speech. And then for the second part of our session, and we will have a breakout to several discussion room as well as we did yesterday, and then to discuss several questions and we have already promoted that. So this is the today's the speaker, and we will start with Tor Hattermann, and he will talk about the impacts of Antarctic meltwater on ocean circulation. And Tor is a physical oceanographer at the Norwegian Polar Institute, and he is leading the section of oceanography within the Institute of Research Department. So I think everybody knows this very well. And then I think now we can let Tor to start his talk. So I will stop share the screen. So probably we will have a around 20 minutes talk, and then we can have a 5 minutes discuss after the talk from Tor.
All right. Thanks so much. I hope people can hear me, and thanks so much, Lou, for this kind introduction. Yes, impact of Antarctic meltwater on ocean circulation. I was really inspired by this subject and to prepare the talk. And when I prepared the talk, I was a bit overwhelmed because this is a wide subject, and I hope you will bear with me through what might look like a little bit of a grand tour, because meltwater is impacting the ocean in many different ways. And just to wrap my head around this, I put up this sort of comparison of scales in time and space, and mentioning in the bottom row kind of a few key processes that I think are relevant here to consider. I just wonder if you all see my Zoom stuff on the screen here. That's a bit annoying. Yeah, let's keep it like that. All right. So yeah, there's sort of on the large scale, there's climate, dense water formation, overturning, sea ice, southern ocean circulation, and then we're getting closer to the continent, slope front, continent shelf processes, ice shelf cavity circulation, and eventually the ice ocean boundary layer processes. And I would call what meltwater does to the ice ocean boundary layer processes also impacts on ocean circulation, because that's sort of the direct interaction. But we come back to that. Then moving a bit closer to the continent, also need to consider that there are different processes dominant in different regions, and I think it's a very useful concept, this classification of the different shelf regimes that you have around Antarctica. In the upper right, there are a few sketches of mechanisms that are important in these areas. The dense shelf regime in the middle of these three columns, which has sort of dense overflows, cold water hugging over the slope, and then the two other extremes where you have a fresh wedge of cold water on the continental shelf, or where you have deep or warm saline water directly accessing the shelf, the continental shelf. And here different physics are at play, so meltwater comes in and pushes different knobs and hinges to do things there. Come back to that, but and maybe take the southern the Atlantic sector of the Southern Ocean as an example, where we have sort of a neighboring dense shelf and fresh shelf regime. Why are they dense? Why are they fresh? I consider this as sort of in the fresh shelf regime, we have a net freshwater import. We freeze sea ice over a larger area and concentrate it at the coast, whereas on the dense shelf, we have a net freshwater export. We're producing sea ice on the continental shelf and exporting this. So that's basically the fluxes here that set up these shelf regimes. And there have been studies that, and you all know this, but suggested how this might change in the future, that there might be a warming happening. And then other studies looked closer into what needs to happen for this. And there are things about the warm water needs to be lifted up. And also there is a density barrier because it is a dense shelf area that needs to be eroded for this warm, dense water to get onto the shelf. And in some future prediction runs, this seems to happen. And then you get into the phase where the meltwater comes into play. Once there is warm water on the shelf, you increase the melting. That prohibits that you form dense water on the shelf because you're adding a lot of fresh water from the melting. And there you are with your feedback loop and your impact of melting on this circulation part. So even if you cool down your climate again, the temperature stays warm on the continental shelf because you can't get rid of or you cannot restore this dense water production on the shelf. That is a very straightforward feedback loop. Then there's this other aspect. You need to get warm water closer to the shelf. I like to describe that as sort of a thermocline depth. You need to lift that thermocline, and there itself is also a potential meltwater feedback further upstream in the way in this fresh shelf regime where you have sort of a frontal system. And from the theory of how these fronts interact, very much known from ACC dynamics, we know that if the density gradient between these two water masses is increasing, then you intensify the overturning, and this is sort of expressed as a density difference here in the for thermocline depth expression that lifts your warm water up. You can see that in high resolution models. When you don't include any sort of ice shelf fluxes, then this balance of overturning is sort of restricted to where things happen. But if you add buoyancy fluxes from the ice shelf melting, then this overturning sort of includes the ice shelf cavity, and suddenly you get a transport of warm water into the cavity and onto the shelf break. So there was a very nice paper sort of synthesizing these two different shelf regimes in this sort of process resolving framework last year. That paper came out, and they sort of looked at how cross-shelf heat transport is responding to gradients in salinity across the shelf break. And so in this center part where it says neutral shelf, there's sort of no density gradient. And if you go to the left, you're becoming increasingly more fresh shelf regime. So and what you see there is this full green line is sort of rate is increasing as you increase the density gradient, and meaning that you get more heat transport onto the shelf, which is sort of a positive feedback if you think dynamically that the freshening acts is coming because of ice shelf melting or meltwater in there. And whereas then on the other side, where you would get a negative feedback, where if you go to the denser shelf region, the denser it becomes, you also get more heat transport. That's sort of a different mechanism. That's this transport upslope because of the interaction of the warm circumpolar deep water with the dense outflow. That effect would decrease if you add meltwater, whereas the green side, if you add meltwater, that would increase. One important thing to note here, this feedback is only indicated by the full line, whereas the stipulated and the dashed line, they are sort of flat. There's no sort of feedback in this fresh shelf regime, and that's really the difference that these mesoscale dynamics in the slope front contribute. This is sort of the eddy component, the eddy dynamics, which drives this overturning. And I like this paper very much because this kind of synthesizes a few things that have been lingering around, but now it's really is demonstrated very clearly, and that's also what they write in their abstract and summary, that there has been not unclarity about whether meltwater would enhance shoreward heat transport, leading to positive feedback, or further isolate the continental shelf from the open ocean, which is what you usually find if you run a more coarse resolution model where you don't resolve these eddy processes. And then from their process resolving study, they find that increased meltwater will increase shoreward heat transport, causing further melt of ice shelves. So this is another feedback sort of tipping point, or however you would like to call it. And because they are productive writers, the same group just recently put out another study where they also propose a mechanism how the Antarctic slope undercurrent may be enhanced and drive heat onto the shelf if you include ice shelf melting. And that's a little bit, it's a different type of dynamics, but it's a little bit what I tried to point at before, that to sort of get the overturning into the cavity, you need to add a buoyancy flux there. And this is just a different manifestation of this process as I would see it. But again, it's nicely demonstrated in this model. So again, another positive feedback found here. So summary, in this Atlantic sector, you might find a dense shelf and a fresh shelf meltwater feedback that is acting there. And then other people looked more into this, finding that these two even can interact. It makes it even more difficult to understand, because suddenly stuff that's happening on the one side of the border is affecting what's happening on the other side of the border. They call this a potential domino effect, with upstream ice shelves experienced increased melt rates, then downstream ice shelves could follow after. Examples of interregional interactions of meltwater have been put forward by other people. Yoshi and Rebecca wrote some papers about that. And there's even another feedback that has been mentioned in sort of a climate model type framework, that simply meltwater increasing the stratification in the upper ocean reduces surface heat loss and therefore traps more heat onto the continental shelf. So there's a lot of interactions going on in this shelf break coastal area. Let's move on a little bit on the scales to the cavity circulation, and just highlighting a more conceptual study here that looked into how melt rates in an ice shelf cavity would respond to a time varying ocean forcing temperatures. And what comes out of this is that the cavity sort of resonates with its own circulation time scale, which is, again, the circulation in the cavity is mainly what is set up by the meltwater itself. So this is a direct interaction, direct feedback with the meltwater that changes the response of the melt rates. And this graph is a little bit difficult to interpret, but basically the gray line is the same everywhere in all the panels, and that's sort of the steady state response. If you on the x-axis have a given temperature forcing in your storing area of your model, then you get a increase of melt rates on the y-axis with increasing temperature. But if you change those temperatures over time, then your response looks like this deformed O shape, and by no means resemble always the respective, or it basically the time mean resembles the time mean, but it's not sort of its phase offset. So this would then impact how we interpret melt rates based on a given ocean forcing that we see somewhere. This can go further on smaller scales. you can run other models with higher resolution, seeing that once the water circulates inside the cavity, it interacts with meltwater. And in this particular case, if you have sort of a warm layer at the bottom and that starts interacting with the ice shelf, it will the meltwater will lighten this warm water, which then suddenly will sit on top of the lighter water, and that together with sort of a local geometry will trap warmer water inside channels, which gives you sort of a channel growth mechanism just because of this this meltwater interaction feedback. Completely without ice dynamics. You just lift warm water up and it stays there because it has become lighter than the colder water below. Yeah, so now it becomes really chaotic because I wanted to bring in some observations about interactions as well. And that's where we have time series from moorings beneath the Filchen-Ronne ice shelf. Looking and there we have pointed out that we see two sort of circulation modes. One is driven purely by sea ice dense water that is produced in this Ronne-Pollinia area, and that propagates sort of through the entire cavity and exits through the Filchner trough. Whereas in other cases, there's sort of a mixed source mode where this flow from the Ronne side is present, but you also have dense water produced in the Filchner trough region that is sort of dominating the circulation in the northern part of Filchner ice shelf. And you see in the time record, this is sort of what we have by now from these moorings from 2017 to today, basically, that these modes are present at different times. There has been a prolonged period over multiple years or multiple seasons where only this Ronne mode was present, and often the Bergner mode is coming in at a particular time of the year. And what is the interaction with the meltwater here is that once you have the Ronne high salinity shelf water present, that is a warmer water mass than the ice shelf water that has come from the Ronne side and has been cooled down to the melting point temperature already. So suddenly you can enhance melting at the ice shelf front, saying that you add fresh water to the system. And just a reminder, we need to remove this density barrier for getting warm water onto the shelf. So if this is happening, and this is how things look like in the temperature salinity space with density contours in the back, higher density to the right. So these two arrows show how sort of a source water mass, high salinity shelf water, either formed on the Bergner side or on the Ronne side, would deform or would transform in the cavity, and sort of the bottom of the arrow shows the product that comes out. And here note that the source waters on either side have different densities, and accordingly the resulting water masses also have different densities. Although the Bergner source and the Ronne product, which is what is meeting at this place usually, they have the same density. But if there's enough Bergner source, that will start producing a lighter product water mass. And if you zoom out from this TS diagram, you see that this Bergner product water mass is actually lighter than the warm water that is away somewhere. So if this mode was sustained, then the system would tend towards something where you would remove this density barrier, the denser water that is on the continental shelf, to allow this warm water to come in. This is apparently not happening because this is still a cold region, and there's also reason for it, because the same feedback producing a lighter water mass from the Bergner meltwater will enhance the stratification on the continental shelf, and by that reduce the formation of the Bergner high salinity shelf water itself. So this is sort of a system that likes to flip back and forth between these states because one state is promoting flip into the other state. And that's what can be seen in the historical data, the R's and the B's are sort of my assignments of when we saw a Ronne mode or a Berkner mode, whereas the center black line, this is from Alessandro's review on the dense water formation around the continent, shows that density in this area has not changed much, although we're flipping between these modes. So there seems to be some compensating mechanism, and that's again in interaction with the meltwater, this stabilizing mechanism. So since this is talking about dense water and bottom water formation, I think now it's time to zoom out a bit and look into the larger scale impacts on sort of a climate model scale. And this is really stuff that we mainly assess from models today and not so much by observations, because this is longer timescales, and this is also you need to have coherent large-scale fields. But what has been pointed out that if you add meltwater from the continent, you're cooling the atmosphere locally because you isolate the ocean from the atmosphere, and you also increase the sea ice concentration. So this goes through the ocean. You get these climate effects. There are also coherent signals in climate models about how things like Antarctic bottom water and North Atlantic deep water formation respond, or I said coherent, at least there's a signal in this model, which was from 2008. And this year there was an update, and there have probably been some updates in between. But basically, people keep mentioning competing climate feedbacks of ice sheet freshwater discharge in a warming world. Here it's mentioned that a positive feedback dominates moderate future warming, whereas if it becomes strong warming, then a negative feedback overwhelms from this particular model. Another initiative that is ongoing, many of you are aware of, is the SOFIA model intercomparison, where it's not being looked at one single model, but a whole bunch of models, more than a dozen. And a consistent response in this model is enhanced stratification, and by that deep ocean warming, as you can see on the lower right, the surface cooling, which is the vice versa effect. Sea ice area expansion is what we saw in the 2008 paper already, a tropospheric cooling associated with that, and a few more complicated steps to get to there, and even more complicated steps to get to stratospheric warming. And many of these effects are sort of not the typical global warming response that we would expect, but maybe counteracting that. However, what the uncertainties? Do we know? How certain are we about this? And we recently started looking a bit into sort of model comparing these SOFIA experiment in the different models with model biases, and that's these two columns with the blue arrows, and then you have the SOFIA anomalies, and then you have the regular warming scenarios, SSP 5 anomalies of deep ocean temperatures. And first thing to note is that the anomalies, that the biases in the models are usually larger or as large as the anomalies that we're looking at. This is not too promising, but still anomalies are consistent in the model. And now the interesting part comes. This is the 1,000 to 1,500 meter temperature, subsurface temperature, and the response in the Antwater anomaly, which does nothing else than adding fresh water, looks pretty comparable in most of the models to what you get in the SSP 585 warming scenario, which does a lot more than just adding fresh water around the continent. So what's happening here, we have not really understood that. We have not really looked carefully into it, but these two experiments in the deep ocean seem to resemble each other. Of course, near the surface, the warming scenario shows a completely different signal than the underwater scenario. It's just getting warmer and warmer. But I'm a little bit suspicious that what we see here might be the effect of increased freshwater input into the ocean in the warming scenario, either from a true signal of the P minus E precipitation over the ocean, or what most of these models do, they have a land runoff routing. Basically, what comes in at the surface goes out right away, which is not what ice shelves do. They need the snow that falls on Antarctica takes a millennia to get out into an ice shelf and melt, but the order of magnitude of this runoff routing increase might by accident be comparable to the Antwater anomaly in a way that this warming scenario might accidentally already include sort of an increased runoff scenario. So this is something that we are looking a bit more carefully into to understand that both good implications and helpful understanding, at least. And what I just said for those subsurface temperatures is also true for the strengthening of the slope current around the continent in most of these models. These two columns are again Antwater, and the SSP anomalies look pretty similar in both experiments. Yes, this was a very quick tour across many of these different scales and different aspects. I'm afraid I might have lost some of the audience just because I couldn't cut short. I could stop here, but I won't. One last thing I want to say, why we should care about these small scales, the stuff to the very right here, the melting at the ice-ocean boundary processes. Simply what this paper nicely demonstrated, if you go out and measure melt rates, you get a completely different results than what we get out of the theory that is used in most of the models. This standard 3 equation parameterization shows sort of melt rates in the order of tens of meters per year in such a warm environment as this has been measured, whereas in reality we measure much lower melt rates below 10 meters per year. And the explanation is that if you increase the stratification in the boundary layer, you isolate sort of the heat from the ice, and it's a little bit same or an analogon of this water droplet on a hot plate. There's really a lot of heat available in this plate to evaporate this entire droplet, but because it creates this little protective boundary layer between itself and that plate, it can survive quite a long time. And that's why these boundary layer, or not boundary layer, but boundary processes are so important for these things that we're addressing here, sort of sea level rise. And the ice-ocean interface itself is such a boundary. You could say that the shelf break is another boundary. You could say that what happens in the coastal polynyas is another boundary process. So we sort of need to pick out these boundaries to understand things. And I think that's where I want to conclude for today.
Okay, thank you. Thank you, Tor. Really good talk about the meltwater that's around the Antarctica. So people who have questions, you can raise your hand, or I saw claps, and also who have this question and maybe have a discussion with Tor can raise your hand. Roland, I saw Roland raise hand. You can go ahead and ask. Yeah, hi.
Hi, I had some Zoom problems yesterday, so I'll leave my camera off. I just had two quick questions for Tor. I was a bit alarmed that one of the projections that you were discussing was in terms of increased meltwater and sea ice area expansion. That doesn't seem to fit very nicely with the last couple of seasons of worrying about sea ice. The only other thing I wanted to say was that, well, I appreciate your remark about the limitations of instant runoff. I think you certainly should revise the timescale for the real world runoff in Antarctica. 90% of the accumulation is quite close to the coast and will flow through the outlet glaciers a lot more quickly than a million years. And secondly, if you're busy melting ice shelves, you can have increased meltwater input almost instantly. And so it could be that those models might be right for the wrong reasons.
Well, I think that last point was what I was trying to get at, being right for the wrong reason. And I was not thinking about millions. I was thinking maybe about 1,000 years, but at least 100.
And the sea ice?
Oh, I didn't write these studies, but I guess what we see today is not only the effect of increased ice shelf melting in Antarctica. It's other things happening that might affect the sea ice.
Okay. Okay, thank you. So Olaf, we can start with your question.
Yeah, thanks, Torge. A really nice overview. Regarding the uncertainties and especially these counterintuitive processes, you came back to kind of observational processes which we potentially could observe. But what would be your suggestion in terms of observations, which tests to perform in order to verify or falsify some of these processes? Especially also because they're varying all across Antarctica, and also thinking a little bit ahead and a large scale to think about Antarctica and things. So what particular suite of experiments would you suggest to remove uncertainties and actually understand where the state of in which state the system is right now and where it might go?
Yeah. Yesterday we talked in our breakout session at least a lot about what should be done for validating satellite melt rate estimates to make those into time series. Thinking completely different here, and where I'm working is sort of this slope form processes, getting multi-annual time series, and that's my input to InSync in many aspects, that what we start in InSync should become a lasting observing time series, at least in some occasions. And then really getting upper ocean seasonality from observations, which we don't have because there are icebergs that drag our moorings away, and well, that's where I burn at least most of my funds these days.
But would you consider rather repeating cruises or just a few moorings? Because we will not be able to put like 10 moorings in a line to observe the whole cross section of the coastal current, for example.
Having ways to extend them above 200 meters into the surface to get the seasonality would be a nice start. Yeah.
Thanks.
Okay, thank you. Thank you, Tom. So yeah, people who have other questions, we may have enough time to discuss during the breakout session. And yeah, so next, our next keynote speaker is Torge Martin, and he will talk about the impacts of Greenland meltwater on ocean circulation. And Torge, you can share your screen. Torge Martin is a senior scientist in the Ocean Dynamic Group at Gilmer Helmholtz Center for Ocean Research Kew, and he runs and advances global ocean and climate model, including regional two-way nesting in the ocean for eddy ridge simulation. So, Torge, you can start your talk.
Thank you, Lou. Thank you for this very kind introduction, and thank you for inviting me to give this presentation. And very much like Torge, I was kind of overwhelmed by the rich literature and studies and observational projects and campaigns that have been run over the past years around Greenland, and also the progress in modeling has been made to cover this area that is of increasing importance for the climate system. So I can only cover parts of it, and because it's my field of expertise, I decided to focus much more on the O in JCIOI than maybe many of the previous presentations actually have. And I will take you a bit away from Greenland during this talk, zooming out of the area. And in this regard, I want to start with this iconic figure that exists in many different versions, but this is basically the subpolar North Atlantic, including the Nordic seas on the right-hand side, east of Greenland, and then you see the Arctic high on top. And from the large-scale perspective, of course, this region is opposing to the Southern Ocean, the other place on Earth where we form very dense waters, where the North Atlantic deep water is formed, that resides below 1,000 or at 1,500 meters and below, and in the Atlantic and global oceans just above the Antarctic bottom water. So the other place on Earth where deep overturning is actually happening. And it's, since we are talking about Greenland, it's of course a story about freshwater release to the ocean. And the subpolar North Atlantic is already a place where there are two competing main water sources. There's salty, warm water from the south flowing northward, and there's fresh, cold water from the Arctic exiting into this area. And maybe Greenland is just a droplet or an additional water source that comes into play. And the question is whether this place can actually tip the scale. So when we talk about this ocean area and the system in combination with Greenland, the obvious elephant in the room is always, will the Atlantic Mediterranean overturning circulation collapse, turning us into driving us into a much colder climate? And there are sometimes some very drastic headlines around that very much like to be picked up by the press. But of course, the story of this region is much more complicated. And maybe the next slide is just a disclaimer about what I will not dive into, the story of whether the Atlantic Mediterranean overturning circulation, the AMOC, is actually weakening. And I will only quickly summarize before I come back to the ice ocean regime that in situ observations of the AMOC made at different places, but most prominently at 26.5 degrees north at Rapid, there's no obvious trend in these data over the past 20 years or so to be seen. And it's quite an impressive record already, covering in situ observations in the ocean, the same place for 20 years. And there were, the last EGU conference, there were competing presentations saying there's no change in the Florida Strait current, or there's a slight decline maybe, but might not be significant. And if we zoom out in terms of time scale, we do that typically with so-called hindcast CIS ocean simulations that are driven by atmospheric reanalysis products, where we can go back typically to the late 1950s to start these simulations. And what these show, and if you just focus here on the black line top or the lines here on top, is that we had in the 1990s a peak in deep water formation in the subpolar North Atlantic, driving a peak in the AMOC. And since then, the system has been declining until today. And the open question basically is how much of this decline is just a setting from this internal variability peak driven by air-sea interaction, by massive heat loss, and how much of it is maybe a decline under global warming, adding fresh water to the subpolar North Atlantic. And if you zoom out further, go to a millennial timescale, then there are proxy reconstructions, and there are groups that provide this message that the AMOC has never been, for the past 2 millennia, as weak as today. And I guess we will see what the future brings, but there are many more smaller scale processes involved in this system, which I will dive to more in a bit. But basically this linkage between a melting ice sheet that adds fresh water to the ocean, thus stabilizing the ocean around and keeping the subpolar North Atlantic maybe from forming dense water, North Atlantic deep water, which then impedes the Atlantic Mediterranean overturning circulation, has made the system one of the key regions of tipping elements in the climate system. And it could be a combined tipping point, but has been decided basically that there are 3 points individually. The ice sheet itself has its own dynamics, of course, and will subsequently maybe impact deep convection in the Labrador and Irminger seas, Nordic seas maybe as well after a while. And this could finally then impact the Atlantic Meridional circulation. Now, over the past 20, 25 years, we all know that Greenland has lost a lot of mass. It has been in a negative mass balance state basically every year over the past years, adding fresh water to the ocean. And the increase, and this is Jonathan Bamber's famous record published in 2018, the freshwater flux from Greenland, total flux has increased in the late 90s, early 2000s by around 40 to 50%. And maybe you can keep this number in mind. This is just 0.01 sphere drops from an oceanographer's perspective. So how much fresh water is that actually that Greenland is contributing that we need to take care of? And there are a few nice review papers, one by a group led by Tom Hayne in 2015, which I use a lot here, that actually the Arctic Ocean reservoir of fresh water is about 100,000 cubic kilometers. And I provide numbers and brackets here, how much change until 2100 the group estimated. So that could become a much bigger reservoir just by river runoff, Pacific inflow. And I guess the effect of sea ice melt is something that we only observed in the early 2000s. Basically, it's a one-time effect because it's formed and decaying in the Arctic Ocean. It's a cycle. And the whole Arctic system can let pulses of fresh water into the subpolar North Atlantic, depending on wind systems happening, affecting the circulation. And one of these, or several of these events occurred in the 1960s and 1970s, called great salinity anomalies. And these provided additional 10,000 cubic kilometers were estimated over 5 years into the subpolar North Atlantic, which really left an imprint there of just internal variability, nothing to do with global warming. And here, this is a number of 0.07 sphere drops. So this pulse is over 5 years per year, then we have a rate that's probably bigger than actually what we see from Greenland now. And in very similar ways, or even bigger than Greenland to the subpolar North Atlantic, would be Arctic Davis Strait export and France Strait export, factor 3, factor 5 bigger. These are actually then the runoff from Greenland. And so the question really is Greenland tipping the scale in some way? Because there are many other freshwater sources that affect the subpolar North Atlantic. And of course, a melting ice sheet has been the idea of really tipping the scale in paleo type of simulations. And there have been many so-called water hosing experiments in the past with ocean and climate models of various complexity. And this is really experiments where you spread freshwater, or people have spread freshwater evenly over the entire region, the subpolar North Atlantic. So really neglecting or summarizing basically all the local and regional processes that could happen because they cared more about centennial, millennial, and longer time scales, bridging all these processes we care about in this community. Even the most recent publication in this respect, looking at a highly complex climate model of higher resolution than usual for the tipping point of the AMOC, they added fresh water not even to the subpolar, but rather to the central North Atlantic to force the AMOC to decline or collapse. So that's not what we're going to do. What we want to know and what we want to simulate and where we need the observation community for is to provide a picture of freshwater release and water mass transformation in the fjords, of course, but really freshwater release around Greenland at all these individual locations. And that's, again, derived from Jonathan Bamber's data set here and high spatial resolution around Greenland, including also a seasonal variability of the runoff and discharge. And there's a strong peak in summer, of course. And this is what has been used much more in recent years to drive high resolution ocean models. And that's what we also do in our group in Kiel, to use this kind of data set. I'll come back to that. So again, on the top left here, Jonathan's iconic figure, basically of the increase of the freshwater flux from Greenland. And based on these data, there are other products coming up. So by Marion Devier, for example, from the DMI, they have a few years back used Johnson's data in combination from the data of Box and Colgan, published 2013, to extend the time series back in time to 1850 to run the classic full historical simulation in the climate models. And we have recently, since the 2018 data set stops in 2016, and to run our simulations to 22, we extended this data set using the runoff published by Slater et al. 21 with the advanced Fern model to extend the time series to 21 and 22 actually. So it just shows how important this kind of data is to the ocean and climate modeling community, and how welcome any additions to these are. And how important it is also shows this graph from the Devilliers et al. Paper, where you see in red basically this curve of freshwater release. And in the background, the timeline of the runoff that the climate models provide lacking a Greenland ice sheet, basically. So what Torge already said, they route runoff or the excess precipitation directly into the ocean. And you see there's much less variability than there actually is in Greenland meltwater and discharge in these kind of simulations, lacking the dynamics of an ice sheet. Speaking of the high resolution spatial meltwater runoff from Greenland, it's of course all the different fjords. And I want to stress the point that in many ways, I see the Greenland fjords a similar issue or a similar field to tackle by the community, like the Antarctic ice shelf cavities. So you have many similar features going on: warm water intrusion leading to ice melt, plume activity at the ice shelf front, topography, so sills that guide inflow and maybe also outflow to some extent. What's probably specific about Greenland fjords is certainly the iceberg and sea ice melange at the surface that keeps the surface always fresh. That's why you also have the meltwater is basically a mixture of this warm, salty or inflow water, then mixed to mid-depth and flowing out, not at the surface. So that's a very important point being stressed over the past years, that just prescribing freshwater to large-scale models at the surface is not the best way to do it, but that's technically what most groups can do. So there are many tiny steps to take to combine the actual knowledge that we have and the local fjord or ice shelf cavity models and regional models to the global modeling and climate community to get these systems combined. And while the sketch kind of stresses that there is no cavity in the fjords around Greenland, I also wanted to show this picture of the 79 North Glacier and the Schaffer et al. Paper from the AVI group, where you actually much more have a system that is somewhat similar to the Antarctic ice shelf cavities. We have an ice tongue or an ice shelf from the glacier, basically in warm water flowing underneath. And while I'm sure there are a lot of local processes that are different, not that much alike, I still see similarities, and where the community, maybe in terms of observational techniques and also knowledge, can exchange a lot to understand both Greenland and Antarctica. And of course, we want to know where the meltwater actually goes from an ocean perspective. And one way to do that is, which is done by a few groups. One is in Bremen, Monica Ryan and Oliver Huhn doing these, using noble gases to track subglacial meltwater from Greenland fjords. This is also the area in front of the 79 North Glacier. This is the continental shelf here, and there are cruise tracks into this area. And you basically see this track here across at the top, and just mind basically the red dots is marking the subglacial meltwater outflow at mid-depth. You see between 100 to 200 meter depth, But what's remarkable, basically, if you look at the map, this map shows dots of the maximum subglacial meltwater concentration in the water column, this place. It's still very high at the fjord mouth, basically. But once you enter the system of the East Greenland coastal current and East Greenland current on the shelf, it's so dynamic that it's quickly diffused and dilutes the tracer. And off the shelf, these black dots here mark locations where there are no significant traces found anymore. In terms of modeling, to resolve this is way beyond climate models. And this is a very nice example and simulation by the group at the Alfred Wegener Institute, led by Claudia Wickele, the phasor model that can zoom into this area. You see, in order to resolve the Rossby radius of deformation, to have mesoscale dynamics in this area, they needed to go down to 1 kilometer and less, basically in grid resolution. You can see this here on the globe. Basically, that's where they can zoom into this area to connect it to the global ocean, which is a very nice feature. But of course, there are many more fjords around Greenland, and there are many more systems that would require this kind of high resolution, and that up to now basically forbids to run this on a global scale, really. And I will come in the next slides to why we also need high resolution south of Greenland. And this is because of where and how the North Atlantic deep water is actually formed, where the overturning, I'm coming back to the AMOC here, where the overturning is happening. And on the top, I show a figure of this textbook picture of the Atlantic meridional overturning circulation, which is a stream function computed from meridional velocities integrated zonally and vertically. And this is, of course, associated with a vertical motion here in the subpolar and polar regions. And while everybody is linking this figure classically to deep mixed layers in the Labrador or Emering Seas or Nordic Seas, so basically a deep mixing of the water mass, the mixing does not constitute any vertical motion. And the vertical motion, this is nicely summarized by Caroline Katzmann from Delft University, is really happening along the boundary. So again, it's the boundaries that we need to take care of and that we need to understand better. And while the water is circulating along the Greenland shelf and around the Labrador Sea, it is densifying. So this is basically a section along the boundary here from east to west. And you see in green colors, light water, and orange colors, dense waters at certain depth levels. So basically, the water at a certain depth is densifying while it takes its way along with the East Greenland, West Greenland current, and Labrador current around here. And why that is happening and why that is important, of course, to create this vertical motion, it's also from Caroline's group. High resolution regional and idealized model simulation showed that there's not only enhanced eddy mixing on the West Greenland side here in the Labrador Sea, where some of these Argo floats stay within the boundary current and others take, basically mixed by mesoscale dynamics, take a route interior to the Labrador Sea. So this is where water from the boundary current is mixed into the deep water formation regions and the deep convection, not deep water formation, but the deep convection regions. But also where actually not only eddies take the water out, but when it's densified due to the deep mixing in the Labrador Sea, and it has the right and matching density of the boundary current layers, it's also the eddies that mix it basically back into its then denser isopycnal layer, and it's carried along from east to west around the Labrador Sea current. And that's actually where it's sinking then. So again, like in the fjords and the fjord outlets, it's the dynamics, the small scale, sub-mesoscale dynamics that drive a lot of these important processes around Greenland, where fresh polar water that is already fresh, even without any Greenland meltwater, mixes with warm, salty Atlantic current waters, but also where Greenland meltwater would then have to play a role and would need to be mixed with the interior ocean. Speaking of high resolution, I also wanted to mention work by the group of Paul Myers. They run very high resolution simulations in ocean models. Here are some 60th of a degree simulations. We exactly see this eddy activity in the vorticity on the west side of Greenland. This is associated with freshwater export into the interior Labrador Sea, as I mentioned, but also with the heat content increase. And this, so the heat is picked up basically from the Atlantic water further out along the shelf slope, whereas the fresh water is from the polar water on the shelf. And this is mixed in the very north of the Labrador Sea, and that's why we don't see deep convection there. But further south, where actually in the green area, convective resistance is much lower. So the water column is much more homogenized, and the heat content is much less because it's ventilated to the atmosphere. And we're just at the verge of really simulating this region properly and understanding all these different processes, also how the Labrador Sea interacts with the Irminger Sea, and I'll come back to that in a few slides. So what we do in our group, in the Ocean Dynamics group at Kiel, is we run these nested setups. So a regional ocean basically embedded in a global ocean, embedded in a global climate model to have mesoscale dynamics, for example, here in the subpolar North Atlantic. And what this helps or aids is basically that you see on the right-hand side I think it's the 10-degree isotherm or 12-degree isotherm in the Atlantic, that if you have high resolution, your Gulf Stream separates much earlier from the coast, takes this well-known northwest corner and doesn't go all the zonal way across the Atlantic. So you get a different size of the subpolar gyre, a different gate width basically on the eastern side of the North Atlantic. And what you gain from this is that you remove this very well-known subpolar North Atlantic cold bias. And it's also a fresh bias, because if your North Atlantic current is positioned too far south, you have too much of this Labrador Sea, cold, fresh Labrador Sea water in this region. Why do I say this? Because this impacts the heat loss and the air-sea interaction in this region, which is the key driver of dense water formation and basically preconditioning of the water mass that then might be affected by additional freshening from Greenland. That's what you can see here. That's a meltwater tracer that actually also with this proved dynamics, we see that meltwater stays mostly within the boundary current, is mixed by eddies in the North Labrador Sea, and then also around the Grand Banks and Flemish Cap and into this area, the Mid-Atlantic Bight. So it's actually mixed into the Gulf Stream extension and then North Atlantic current, and does not, as many cost resolution motion ocean models show, really just take a turn here and go zonally across the Atlantic. I wanted to cover very briefly, I need to speed up a bit, sea level rise. And on the top left here, you see actually that this is the bathtub effect, that if you add mass to the world ocean, you get the global mean sea level rise. But I wanted to emphasize that adding fresh water to the ocean, of course, changes the density structure and therefore impacts the ocean circulation. And what you get from that is a stereodynamic sea level change. And that's what you see here after a century of added fresh water from Greenland to the subpolar North Atlantic, 0.05 Sverdrups. This is so 5 times the increase we have recently observed. And what you see, what I want to emphasize on the left-hand side, there's 3 different ocean models driven by the same atmosphere, showing not only sea level increase in the dark brownish areas, but also decrease in other areas. And these regions differ a lot also how much Europe or North American coast would be affected by the internal dynamics of that model. And if we add or explicitly resolve mesoscale dynamics, we get again a different picture where actually it's mostly the American side that's affected by these dynamic and density changes of Greenland meltwater, not so much the European shelf. So again, ocean dynamic and ocean grid resolution matters even for the projection and forecast of regional sea level change. And to continue on the story of how coupling and resolution matters, I've run 4 simulations with our coupled climate model at half-degree non-eddying, at high resolution nest, and then the same setups basically forced by the atmosphere. So not interactively coupled. And I jump over and show you that actually the coupled simulations show much less AMOC decline, 1.5 to 2 Swerdrups decline compared to the ocean-only forced experiments. So we asked ourselves, what is the reason that these 2 different model types, they're both used to estimate the impact of Greenland melting, that they respond so differently? And because both systems, on the left column, the coupled one, right one, the forced one, show surface cooling with a weaker AMOC, less heat transported northward. That's what we expect. But with the cooling, there comes a strong decrease in surface heat flux or heat loss of the ocean. Whereas in the coupled system, atmosphere and ocean system adjust. So the heat loss of the subpolar North Atlantic stays back the same after a few years of adjustment. And the driver of the AMOC decline or variability is not as much affected as in the ocean-only simulations, where the cooler ocean is getting closer to the wintry cold atmosphere, and therefore you get a smaller temperature gradient and less ocean heat loss, which then is a positive feedback that's adding into a sharper decline of the AMOC and these kind of uncoupled models. And one other issue about boundaries and scale and resolution I wanted to mention, because this is a nice combination we can do now with the model runs of Klaus Böning and group in 2016. And the colors you see are just meltwater tracer from Greenland, so you don't need to bother about the details. Red is a lot of meltwater, green is not so much meltwater, and it's after a few decades of meltwater release. And what I mentioned earlier, on the very left-hand side, you have a half-degree non-eddying ocean, but with eddy processes parameterized. And then you have a quarter-degree ocean that does not really resolve mesoscale eddies fully in this high northern latitudes, but still the mixing is turned, the additional eddy mixing is turned off. And then a 10th or 20th degree resolution where you have more and more eddies in the ocean. Just to highlight here in these circles, again, the northwest corner dynamics where you have the North Atlantic cold bias, that really it's ocean resolution that can improve this region. It's not the eddy parameterization that can help very much here, but it's on the very right-hand side showing if you have mesoscale dynamics, you get this area much more properly resolved, and also therefore the pathway that Greenland meltwater takes. And if you go to the Labrador Sea, that's actually where you find that this mixing between the fresh boundary and the salty interior, the sharp density gradient, that's something that the Jet McWilliams eddy parameterization can handle very well. That's where it's designed for. That's why the half-degree model actually almost performs as well as a 22-degree high-resolution model, whereas a quarter and even a 10th of a degree is insufficient to get the right mixing from the boundary. And just last slide here, wanted to stress this, what's happening recently in this region. And there was a paper by Sian Rues showing that in the deep convection in the 1990s in the Labrador Sea was very intense, then calmed down basically in the late 90s, and recently picked up again, but in much more easterly direction. And we were wondering whether this shift has anything to do with more fresh water coming into the northern Labrador Sea here, because this area is linked mostly to what fresh water comes along Greenland. Here, the brownish colors, you can see basically this large internal variability and decline of the recent years where Greenland runoff increased, whereas the green dots here coming to the southern Labrador Sea are mostly forced by salinity variations in the eastern North Atlantic, where only in the very recent years you see some propagation of the eastern North Atlantic freshening. So 2 different areas driven by 2 different freshwater sources or salinity variation sources. And running two simulations, one basically with the observed increase in Greenland runoff and one with a climatologically continued runoff from the mid-20th century, we see that actually Greenland meltwater forced the boundary current to speed up a little. It's not much, but it's significant. And that actually this very eastern shift of the deep convection is partly driven by the meltwater, because with meltwater added, the elevator in the Labrador Sea doesn't go as deep, but then propagates a fresher mode water into the eastern Ilmenau seas, where it destroys stratification. You get a bit deeper mixing. And with that, I would like to conclude, and these are my take-home message. And yeah, happy to take any questions and looking forward to the discussion. Thank you.
Thank you, Torge. Thank you for your whole kind of the talking about the meltwater that around the Greenland from different aspects. So people who have any question, you can raise your hands or just directly open the mic and then have a discuss with Torge. Yeah, I saw Sue.
That was really interesting, and I've been thinking much more about Antarctica recently, so I apologize, I'm not very knowledgeable, but I hadn't appreciated how much fresh water there is from other sources in the Arctic, and other data from those kind of salinity events in the past from other sources that help you to understand, like, if Greenland did suddenly start really increasing output, how that might impact. Is there enough to be useful?
Certainly, yes. Especially the great salinity anomalies were relatively well covered and documented, I must say, for these early days, considering that we are all puzzled by the Weddell polynya in the very first satellite records. So we do have a bit better coverage in the subpolar North Atlantic. And we can see from the grain salinity anomalies how they propagate actually around the subpolar gyre. And I think that's something that we need to consider for enhanced Greenland melting as well, that there will be most of the meltwater will actually just propagate around the subpolar gyre. There's only in combination with favorable wind along or on the Greenland coast that drive corresponding Ekman transport and with the right eddy mixing, you get a node of this additional freshwater into the Labrador seas. But I mean, that was my perspective, was that there must be or could be soon an impact by Greenland meltwater. What I learned about during the last decade is really that the atmosphere is a very strong driver of variability in this region, because there is and always will be and always has been relatively fresh water in the boundary current around Greenland. And it's like with a circumpolar deep water around Antarctica, there is a lot of heat. We don't need global warming. There's a lot of heat. It's not about additional warming. It's not about additional fresh water, about changing the local dynamics.
Thanks.
Thank you. Christine, you can go ahead with the question.
Yeah. Torge, thank you very much for the talk. I'm interested about your perspective of, what's the difference between West and East Greenland, or let's say North or West of the Greenland, Scotland Ridge. Would you separate these areas in different dynamical regimes in terms of the vulnerability of the fjord systems where glacier at the end are coming in contact with the ocean?
It's a good question. Yes, I would separate regions. Excuse me. Starting with East Greenland versus West Greenland, I need to emphasize that so first the outflow, basically the meltwater of East Greenland is what could impact the Ilmenau and Labrador seas directly. West Greenland is really going into Baffin Bay and then mostly recirculating with the Labrador current. In terms of being affected by warm water intrusions. I mean, in the Ilmengar Current further offshore, there's a lot of warm water in southeast Greenland potentially available, but then again, there's a strong barrier with the coastal area, also in dynamics and in density, so that I would think, or that's speculation, but I would think that actually we might see in northeast Greenland rather intrusions of warm water. So just because the barrier is so strong in East Greenland, the coastal current and the East Greenland current have so high flow speeds, there's very little mesoscale dynamics compared to Southwest Greenland. It's going to be an interesting region, maybe in a few fjords, and that might stress that wherever you are around Greenland, that the local fjord topography matters a lot, that there are large fjord outlets that have troughs associated with them, might have water exchange along the sloping topography into the fjord that kind of connects under the boundary current or the coastal current. That's something Renske Gelderloos, for example, simulating in Delft University. Very interesting stuff. It says a lot about going fjord by fjord, like going ice shelf cavity by ice shelf cavity in the Southern Ocean.
So it sounds like, again, regional details really matter. Okay, thanks for your view.
And I mean, hydrography matters, but topography, bathymetry, really, we need to know the bathymetry. So whenever you go out measuring, whenever you have any instrument glider that you run, we need better maps, I think, wherever we can do that.
Thanks.
Go ahead, Roland.
Oh, that was certainly a massive tour in.
Yeah, sorry for that.
No, it's great. Just in geography and in physics, I think. I just had a technical question about your sea level simulations. Did they also involve the Greenland gravitational effects on sea level?
No, they don't. And I think, again, and that we have another working group on that going on, combining fingerprints of ice mass loss and sea level rise is, I think, an important issue. Spatial fingerprints and also on the temporal scale. What is basically I mean, from Greenland, as much as I understand, in the first years, we will see sea level rise along the coast due to the added mass or volume to the ocean also and circulation change. But then the solid Earth will basically start to lift due to the reduced mass of the ice sheet. And we see sea level decreasing locally around Greenland. And how far that actually reaches in the subpolar North Atlantic is quite interesting. In magnitude, it's not that much different from what I show here as the stereodynamic sea level change. So we might see competing effects over the next century or two or so. I mean, if we don't see it, but
sure,
our children will see it.
Just distinct from glacial isostatic rebound, though, there's the gravitational effect that the sea level will typically fall around Greenland because there's less ice there attracting the ocean.
Yeah, that's true. And we don't have that even included in these kind of simulations, impacts on ocean circulation. So, but there are fully coupled systems coming up at certain and at several centers within the next 10 years. They're certainly operational, I would think.
Yeah, thanks. It was just a clarification. Thanks.
Thank you. Thank you all. So for that, we can wrap up our this keynote session. In fact, thanks Tar and Todd talking about the Antarctic and Greenland meltwater on the ocean circulation. And we will move out to the breakout discussion part.